Everybody. Thanks for joining today's NC-CAV seminar. It has been a while that we didn't have a seminar during the summer, and this is our first seminar in fall semester. As you may know, the last Friday of every month we do have these NC-CAV seminars. Thank you for the sponsors of the project, North Carolina Department of Transportation, as well as the other sponsors, Data Greensburg, Verizon, and Real-Time Innovations, RTI. Today we are delighted to have Dr. Arman Sargolizai as a speaker. The title of the talk is Testing and Verifying the Security of Connected Autonomous Vehicles. A little bit about Dr. Arman Sargolizai. He is currently an assistant professor of mechanical engineering at University of South Florida. Dr. Sargolizai's expertise is in applying linear and nonlinear control models and methods, machine learning, and artificial intelligence to the field of cyber-physical systems. His mission is to enhance the quality of life for people by assuring safety, security, privacy concerns through extensive collaboration among multidisciplinary fields. He has received more than $1.5 million from different agencies, including NSF, NASA, and others. He is the recipient of NSF Career Award for his research on testing and verifying the security of connected and autonomous vehicles. He has published more than 70 articles in high-impact journals, and he is the associate editor and in some of these journals, such as IEEE Transportation, if I'm not mistaken, right? Systems. So with that, I'll pass it to Dr. Sargolizai.
Okay, thank you. So let me start sharing my screen and start my presentation after that. So can you guys see my screen correctly?
Yes.
Okay, let me see if I can minimize this for myself. Just a bit weird, WebEx, I haven't worked with it. Okay, so hopefully it's working now. Can you see everything?
Yes, we do.
Okay, great. So good afternoon, everyone. This is Arman. My last name is Sargolizai, which is a hard last name. So everyone, they call me Arman. I'm right now at University of South Florida. So this is my first semester at University of South Florida. I used to be at Tennessee Tech University for almost 2 years. And before that, I was at Florida Polytechnic University for almost 4 years. And I was also director of Advanced Mobility Institute at Florida Polytechnic University for almost a year before I moved to Tennessee Tech. My research background is about security of connected autonomous vehicles in general, security of network control systems, and then one of the main application of our research is on connected and autonomous vehicles. So my field, I mean, I have a multidisciplinary background, but myself, I used to be in electrical engineering field I got my basically bachelor, master, and PhD in electrical engineering, and after that, I wanted to know more about mechanical aspects of my research. I started my mechanical engineering and aerospace engineering after that. So in my field and in my research group, we have also several different students from different fields. I put their picture here because they are really key people in my research. I used to have more students. These are the only ones that I could transfer with myself to USF. James is one of my PhD students. His background is in computer science, and now he's doing his PhD in mechanical engineering. Parissa's background is in electrical engineering, and she's working right now in mechanical engineering department. And Hamed is also in mechanical engineering. I think one person didn't mute, so I can hear background noise. Yep. So in order to talk about the autonomous connected vehicles, we all heard about connected autonomous vehicles that they said we're going to have this autonomy and autonomous vehicles in maybe 2020. Right now we are 2020. We heard about 2030. We might have some autonomy by 2030 and so on. But one of the main reasons that we want to have autonomous vehicle is to improve the safety. But there are a lot of challenges with safety of autonomous vehicles. One of them is testing and verification of those vehicles, how to make sure those vehicles are safe. And on top of that, security and privacy of those vehicles is another big challenge which we are going to have down the road. Unfortunately, in a smart grid, for instance, or other like a major critical infrastructure, they started to build all those networks, all those systems, and then later on, they started to think about security and privacy aspects. So fortunately, in connected autonomous vehicles, we started to think about it at the beginning and in a right timing, and hopefully this is not going to be the same situation in the future. Let me share a quick story with you guys. When I was in Florida, I used to live at basically Gainesville, University of South Florida. You can see it on top of this map. And my university, the one that I was a faculty member, it was Florida Polytechnic University, which was in Lakeland, South here. Uh, Between Gainesville and Lakeland, it's about 240 miles going back and forth. So it means 120 miles each way. And I used to go this back and forth almost every day except Fridays for almost 4 years. So it was rough. It was hard to really go back and forth between Gainesville and Lakeland, but I did it because I was doing my second PhD at Gainesville, and also I was a faculty member at that time at Florida Polytechnic University, so I had to go back and forth between Gainesville and Lakeland. So why I'm sharing this, I'm trying to say I drove a lot. Like in one of my car, I drove almost like 200,000 miles, and another one is 150,000 miles, and I drove a lot. And if someone could come to me and would say, hey, having an autonomous vehicle would be great, so you wouldn't need to drive this much, I would say, yes, definitely, that's going to be a great like advantage for us because I can do other things. I can write papers, I can grade the students, let's say, papers. I could talk and I could have meetings with other students and my colleagues. And it would be great because at that point, having an autonomous vehicle, it would be really great for me and my situation. But I would probably, if they would try to give me a free, let's say, autonomous vehicles, I would think again about accepting it because there is a huge problem with testing and verification of those vehicles and those systems. And one of the major issues that we are focusing on is security and safety of those vehicles, how to make sure they are safe and secure. When I was going back and forth through Gainesville and Lakeland, I witnessed a lot of different situations that we didn't know how to. I mean, as a driver, I didn't experience those situations before, but we as a human being, we could really come up with different strategies in order to tackle those challenges. And I would add here, despite the fact that some people they are saying autonomous vehicles they are great, they are better than human. My personal, so I'm not really extended to other people, but my personal opinion is that human drivers are the best drivers. The only problem that human they have compared with other, let's say, autonomous vehicles and other technologies, the fact that our sensing environment is limited, and also we get distracted, we get tired, and we face some other issues that is going to cause some accidents or collisions. So there are a lot of challenges with basically technology like autonomous connected vehicles and testing and verification of those. One of the main challenges that we have is the fact that how we are going to test those vehicles, how many scenarios we have to generate. Do we need to test the vehicles for all different possible scenarios or different possible situations? The answer is no. We don't need to really test for all different situations. We have to really come up with some sort of mathematical framework in order to differentiate those from each other and find equivalent classes and also come up with coverage analysis in order to address this issue. There is another big challenge, which is their accidents, real world accidents. Currently, we already have current accidents or real world crashes, which is happening in the United States and other countries. So the challenge here is how we can learn in a systematic manner from these already happened crashes and test future vehicles against those scenarios. So that is something which is missing. We have for traditional vehicles, we have some sort of, let's say, scenario generation that we're going to learn from previous crashes and we are going to test the vehicles or test the infrastructure. But for autonomous vehicles, we are working on that. And that's one of the big challenges, how to learn from already happened crashes and generate new crashes. We also have problem with sensors. In my research, we are not focusing specifically on sensors by itself because manufacturing, they're doing that and companies, they are working on testing those sensors. We are trying to look at the effect of or impact of sensor failures in decision of vehicles. So how how an autonomous vehicle is going to perform under lightning, snow, heavy rain, which we have it a lot in South Florida and also Florida. We have lightning, we have fogs, we have rain. You guys experience the snow in your area. So how we are going to learn from those, how we are going to test the vehicle under those situations. Do we need to really come up with individual testing for different sensors, which in my opinion, we don't need to do that. We have to really look a bit on a higher level as far as testing those sensors. We don't need to go lower level testing for sensors. Let's say there are issues with sensor fusion that we have to test as well. One of the scenario that I can mention, one of the company, which I don't want to mention their name, they want to get rid of LiDAR. So all these different sensors, they together, they can work in, they can be robust and reliable. So if that specific company, they get rid of LiDAR and they just use camera, then they are not going to perform fine in rain, snow, or let's say foggy situations. So how we are going to test those situations, how we are going to come up with scenarios to test those situations related to sensor failure or sensor faulty sensors. The other challenge that there exists is how we make sure connected autonomous vehicles are ethical or basically they are doing, they can interact with human beings. This specific area is not my field of interest or field of research, but this is really a this is a really huge challenge which we are going to have in the future because at the end of the day, autonomous vehicles are going to work with human being and they are going to have interaction with human. How we're going to test those interaction? How we're going to make sure that an autonomous vehicle is going to learn the language of driving because all of us as a human being, we have language of driving. We look at, we have like eye contacts, we use our hand, we use gestures, we use different sign when we want to drive. So how an autonomous vehicle is going to do that? And also from the aspect of being ethical, how an autonomous vehicle is going to make a decision, which one is safer, what decision is safer, what decision is ethical. So how we're going to test those situations. Again, this is not my area of expertise, but this is another challenge that we are going to have with connected and autonomous vehicles in the future. And finally, which is the area that I'm working a lot with, is security challenges. We have a problem with the fact that we don't know when, where, and what type of attacks are injected or basically are affected our connected autonomous vehicles. So we need to come up with some sort of solutions that doesn't really require identification algorithms that I'm going to talk here about is how to look into the impact of attacks or effect of attacks instead of a specific attacks. We all the time we have challenges with the random type of attacks, constraints with the resources, and intelligent attacks. Attackers are and adversaries, they are not sitting there. They are working full time on generating or finding new vulnerabilities on CAVs or transportation systems. So we need to be also really, we need to also work hard in order to tackle those issues. In my ethical hacking course, all the time I'm mentioning to students that we can come up with really great, for instance, for communication, we can come up with really great communication protocol or really great let's say security algorithms that is going to be secure, and it's going to be great. We are going to add really great and powerful encryption. But the main problem with that is delay and time, and also some being user friendly and not being user friendly. Those are the situations that we have to really think about it when we are designing security countermeasures. So for testing connected autonomous vehicle, we have several different regimes. One of them is software in the loop, which is offline testing. This software in the loop and offline testing is great because we can test a million of scenarios in a matter of seconds. But the problem with that is it's not realistic. It's not really real time. So there are software in the loop which is in real time mode, which is going to be better. It's going to be more realistic. But again, at the end of the day, software in the loop in real time mode is not as realistic as hardware in the loop in real time. And also we have real world testing, which is in my opinion, is the best type of testing as far as being reliable and also being realistic. But the problem with real world testing is the fact that we cannot test against all different situations. Imagine a scenario that, let's say, a vehicle is approaching an intersection, and in the intersection there is a pedestrian. Then we want to look into the interaction between uh, vehicle and pedestrian while there is an attack on the vehicle or there is a cyber attack on the actual car. So how we're going to test that in a safe environment, in real world environment, is hard and challenging because we don't want actual collision to be happen. So we can, I mean, basically people, they're using vehicle in the loop environment. The problem with vehicle in the loop environment is the fact that it's a great testing environment and testing platform. But the problem is that this interaction is not realistic as well. So we came up with another type of testing platform that my student actually they like to call it mixed reality platform, which is going to combine the vehicle in the loop and real world environment together. I'm not sure if I can show you using my highlighter here. So if you can see here, this is our real world environment or real vehicle, which is a passenger vehicle. So we also can do this with trucks, shuttles, and other vehicles. We have a performance assessment unit here, which is going to measure the safety and security of vehicle in different scenarios, and it's going to generate outputs. One of the output goes to scenario generation, and one of the output goes to the adversarial simulator, which is going to generate different type of attacks. So this loop is going to be in real time, and we are going to generate harder and harder scenario based on performance of the vehicle under attack and also under different scenarios. And this is going to continue. And my main objective, or basically our main objective here, is to fail the vehicle, basically forcing the vehicle to act in an unsafe manner. So the scenario generation is going to generate scenarios based on three different modes. One of them is the digital twin generation. Another one is based on already happened crashes, which I'm going to show you a video demonstration in a second. And then the third way of generation of scenario is based on machine learning and also edge case scenario generation, which is going to generate scenarios, which is going to be harder and harder in order to make the vehicle to be fail. So through the scenario generation, we're going to generate a simulated environment, and simulated environment is going to have other vehicles, other pedestrian, but a good feature of this mixed reality is that we can have another physical vehicle and we can embed that physical vehicle in another, let's say, parking lot. Let's say if you have two parking lots and we want to look at the interaction of these two vehicles with each other, we can have one in parking lot, one another parking lot, and we can interact them in a virtual environment that we have. We are going to generate the simulated sensory information. We are going to have the real world feed of sensors, and we are going to mix them together using our sensor hardware in the loop environment. And then the combined data stream, it goes to our decision and control center, and it's going to control the vehicle under those situations. So we have a feedback here, which is really high, prestigious, and accurate IMU GPS, which is going to send all this real-time information on vehicle dynamics into our simulated environment in order to make the interaction between vehicles with other vehicles, vehicle to pedestrians. So in order to show you what exactly this means, I think this video is going to help you with, I hope the sound works, but let me know if it doesn't. So can you guys hear the voice?
Yes, we do.
Okay, great.
Hello, my name is James Holland, and I'm a graduate research student working with Rank's lab at TN Tech. Today we are unveiling our latest addition to the research fleet. This unassuming Ford Fusion Hybrid comes equipped from the factory with advanced driver aids like 360-degree proximity sensing and adaptive cruise control. Thanks to the expertise of our partners at Autonomous Stuff, IPG, and Genesis, the vehicle has been equipped with integrated I/O and converted into a development platform ready for research. This short preview is recorded during our initial testing with the vehicle. In this scenario, the Fusion's ability to detect and react to a simulated vehicle will be tested. As can be seen, the vehicle comes to an abrupt stop, but seemingly for no reason at all. While this is true, we can see from inside the vehicle that the simulated scenario is running. This causes the vehicle to believe that it is actually driving on the simulated road and reacts accordingly to the simulated vehicle.
So that was one of the videos that we basically we did a test a year ago for demonstrating AEB testing, or basically automatic emergency brake system in normal situations. So I'm going to show another one in a few minutes about how to test it under different type of attacks. So for scenario generation, as I mentioned, we can use digital twin environment. We can use scenario abstraction using real life or real world crashes, which in this case, you can see we collected almost like 100 different accidents or crashes in United States. And we look at the crash database and we look at the report, like a police report, and we just extracted all those using natural language processing. And also we extracted weather information at the specific time of the crash, some traffic information, and we simulated those as a first scene of, or basically initial scenario for our scenario generation, which we are using it for testing the vehicles, and then using machine learning, we are going to come up with different variation of those scenarios. So this database is open, so anyone wants to use it, there's a website, my website, and you can download the scenarios and you can test the vehicles or different vehicles using that scenario. So this is the demonstration. I'm not sure if we have enough time, but I'm going to show just some of these demonstration about this real-world crash scenario generation.
Involving autonomous vehicles factors into account to produce a more accurate representation. Institute.
So this is the website that we have, and we collected all the crashes with description of them, location of them, and also we generated simulated of those scenarios. All the simulation are in MATLAB and it can be used for different purposes.
The Advanced Mobility Institute, or AMI, has gathered a total of 96 incidents involving autonomous vehicles. The details of these incidents come courtesy of media outlets and the California Department of Motor Vehicles. The description and locations of these incidents are logged in the AV database. Once a simulation is created, the database is updated with a preview of the simulation as well as a downloadable zip file containing the necessary code to run the simulation in your own MATLAB environment. Recreating an incident also requires map data of the location it occurred. OpenStreetMaps is an open source effort to create a free, editable world map. More importantly, however, is that this map also contains data and information for roadways, such as speed limits and roadway geometry. By using OpenStreetMaps, we are able to gather all the necessary data to reconstruct the roadways in question for the placement of vehicles in the simulation. To process an incident and recreate it, the system first would retrieve incident locations and details from a centrally managed database. Next, the system would gather a map of the area in which the incident occurred. By using NLP, the text data related to the accident can be processed to create a script of what occurred. With the main roadway in question identified, the system can determine any features of the road that may have increased the likelihood of the incident. Following the script, the system then plots the vehicles and their paths on the map. Finally, with the map data processed, actors defined, and roadway features identified, the simulation can be run. The simulation's primary concern is the autonomous vehicle and any vehicles or pedestrians directly involved in the accident. These actors' paths are gathered from the incident description. To create a more realistic portrayal of the incident, the roads are also populated with extras that are simply following the predefined path of the road.
So that was related to this scenario generation, one of them. And about the attack generation, as I mentioned before, instead of looking at different type of attacks, we look at the impact of attacks, and we generate the impact or effect of attacks in order to make it more general as far as attack generation, or basically false generation. So this is one demonstration that we have for AEB under false data injection attack, that we injected like some faulty information or faults to the radar information or radar data. See how I can play this. I'm going to skip it to here.
More secure in recent years. Connected vehicle technology is still new, untested, and unproven. Just as was the concern with insecure physical systems, insecure communications can result in widespread disruption and chaos when an adversary injects a malicious message or causes a delay in vital communications. The foundation of the system is a passenger vehicle that has been extensively modified and outfitted with a completely programmable drive-by-wire kit and high-precision GPS and IMU. This kit, coupled with IPG's real-time target machine and carmaker software, allows for the vehicle to be placed into a virtual testing environment while also carrying out its actions and decisions in the real world. The importance of this aspect cannot be overstated, as it allows for real-world vehicle dynamics and motion to be fed back into the simulation in real time. To demonstrate what vulnerabilities look like in the real world, we will subject our platform's automatic emergency braking system to a false data injection attack. The attack will increase our virtual radar signal data such that our vehicle appears slower and further away from the leader vehicle. This will be illustrated with 3 test runs, one under normal conditions, another with an increase of 1 meter per second, and lastly, a test with 2 meters per second. This is our control run. Notice the car's stopping position relative to the marker. Next up is our first attack run of plus 1 meters per second. The vehicle stops slightly later than the control run. This last test is with an increase of 2 meters per second and makes the attack effect quite apparent. As illustrated by these 3 tests, false data injection attacks impacted the algorithm's ability to safely stop our vehicle and demonstrated its vulnerability to attacks and disturbances.
Okay, so that was related to AAV under attack.
Thank you for your time.
And also we develop our own CACC algorithm, the cooperative adaptive cruise control algorithms. As you know, CACC are also vulnerable to different types of attacks, such as false data injection attack, time delayed search attack, denial of service attack. So in this specific demonstration, we develop a new kind of like cooperative adaptive cruise control algorithm, which is going to use a combination of machine learning algorithm and also model-based algorithms in order to detect the amount of attack in real time and also compensate for that in real time. And then we implement it using our passenger vehicle, and we demonstrated that we can compensate the amount of attack injected in real time.
My name is James Holland. Attack. Control algorithm performs against adversarial attack. In our test scenario, both the test vehicle and the simulated lead vehicle will accelerate to 3 meters per second. 15 seconds into testing, both vehicles will accelerate to 6 meters per second. 5 seconds later, the lead vehicle decelerates to 3 meters per second, and after another 5 seconds, a simulated FDI attack is injected. The FDI attack increases the leader's acceleration reference signal, leading the follower vehicle to act as if the leader vehicle is traveling faster than it actually is. In the case of a traditional controller, such as a PID, this will likely lead to a collision between the vehicles. Our observer-based controller, however, is designed to not only detect, but to also mitigate such attacks. The follower's controller uses the leader acceleration as a reference signal to determine whether the lead vehicle is accelerating or decelerating. Using this, the distance between the vehicles is derived and used as the set point for the algorithm. A neural network monitors the reference signal to detect and estimate the magnitude of faults and attacks to produce an error signal to mitigate any disturbances. The observer also monitors the signal in order to estimate the true system states to define a control signal appropriate for maintaining a safe following distance. Testing will be performed on our research vehicle by uploading a model to a micro Autobox 2 that interfaces with our test vehicle's CAN bus to receive sensor measurements and send actuator commands. Our model was developed in MATLAB Simulink and uses the DSpace RTI CAN block set to interface with our vehicle's actuators. By using a DBC file, our model is able to translate the control signal into CAN messages. In the following plots, various performance metrics are displayed for comparing our observer-based controller against the traditionally designed counterpart. When under attack, the traditional controller perceives the lead vehicle to be accelerating, in turn producing a control signal that increases the follower's speed. However, in the case of our controller, the follower immediately begins decelerating to match the lead vehicle's true behavior. The effects of this attack are made apparent in the following distance measurements. The traditional controller predictably collides with the lead vehicle, as shown by crossing the x-axis. Our controller, however, successfully prevents collision and maintains the desired following distance throughout testing. Thank you.
Okay, so that was related
for
to
dropping by.
our CACC. We do work on several different projects. One of them is we have our driving simulator. So unfortunately, I couldn't move this one from Tennessee Tech to USF, but we are designing and developing another one at USF right now as far as driving simulators. So we are trying to also make it some sort of with 6 degree of freedom in order to have it. And also we are going to install some of the sensors that we are purchasing, and we are going to make it level 2 plus, hopefully in next 1 or 2 years. We are working with a Formula race vehicle as well. So I'm an advisor for Formula SAE. I used to be an advisor for Formula SAE at Tennessee Tech, and I'm a Formula advisor at USF at this point. So one of our main project is to come up with autonomous race vehicle as well for robo racing competitions. So that is one of the main projects that we are working. We also work on off-road applications such as golf cart, tractors, and some other like off-road applications for making them automated in order to also test the automated features for off-road applications. So we do our main projects or main focus is on testing and verification of safety and security of connected autonomous vehicles. We do vulnerability analysis. We demonstrate the attack impacts on CAVs, and also we improve the existing algorithms, existing control algorithms, and autonomous algorithms to make sure that they are safe and secure under different types of false failures and attacks. So I'm going to stop here, and if you have any questions, I would be glad to answer those.
Great, thank you so much. Very interesting talk. So, any question?
Well, I'm sorry, I was struggling for up to now about 40 minutes to log in. And I missed your presentation.
So I think there is a recording, so definitely you can take a look at that. You can send an email to me if you have any questions. We can also like schedule or create another meeting and we can talk.
Sure.
Great. So, while others are warming up to ask questions, I'm going to go ahead and ask one question regarding to test and evaluation that you do have. I realized the kind of the simulated environment or different approaches that you had, virtual reality and other approaches that you were creating a platform that you can start testing and evaluation. But the framework that you are using for test and evaluation, what is your approach for testing and evaluation to it? And what is the primary specifications or property you try to test and evaluate?
So basically our performance unit, the unit that I showed for performance is going to, at this point, is going to look at only at safety measures. So safety measures, we define them by ourselves. So it can be, let's say, a speed limit. It can be, let's say, distance between vehicles and other objects. So we define those performance measures, and then we are going to generate scenarios and also generate attacks. And we are going to look at those performance measures or performance matrices. And we're going to use reinforcement learning in order to generate harder and harder scenarios and attacks in order to make the vehicle to be failed, or basically make the performance measures to minimize the performance measures, because minimizing them for us means the vehicle is not safe enough. So that's one of the things that we are doing. Another thing that we are planning to do, we are coming with a different type of security measures, like different, let's say, parameters in order to check how secure is the transportation system in general. Let's say transportation system, what I'm saying is vehicle that is communicating with other vehicles using sensors or using like communication channels, or vehicle that is communicating with infrastructure and pedestrian in the sensory network. So we are coming with different type of, let's say, measurements, which I can share with you some of the papers that we have related to that. And then we are testing also those parameters and those measures in order to generate harder attacks or more complicated, let's say, combination of attacks.
Okay, great. Thank you.
I have a question, Arman.
Sure.
Thank you
Sure.
for the presentation. Regarding the false data injection attack, you showed that radar data was getting altered. Like, I'm not talking about like university demonstrations and things that are useful in its place, but do they really, like, is it really possible that with like encryptions in place on ECU, TCU, and then we have those kind of attacks?
So false data injection attack is going to be a bit harder as far as like when we have the communication, we have the encryption. But some other attacks like let's say denial of service attack or time delay switch attack, that we are just delaying the packets when we are transmitting those information from one location to another location, that is possible. And I would add also, FDI attack is also possible if someone get physical access or hardware access to the vehicle. Let's say a malware that is installed in the computer of vehicle, so it can do that. So when the packets are transmitted and they are received with the vehicle, so if someone has access to that, they can also manipulate the information and create false data injection attack. But as far as your question, when it's encrypted and we are sending using DSRC or let's say cellular CV2X, it's going to be a bit harder because it's going to be, I mean, it can be done. So people, they are doing man in the middle attack and they are injecting false data injection attack. But the problem is the cost benefit analysis that the cost benefit analysis doesn't make sense that someone really hack the communication between vehicle to another vehicle and encryption of that in order to malfunction something.
Okay, thank you. And regarding maybe relevant question to what you are telling now is that, like, even denial of service attacks, have they happened outside research domains by like actual malicious actors
Yeah.
so far? Because um I have attended many events with industry experts, and the general uh, the general thinking is that these do not happen because have not happened, and it's just some universities or some national labs that have done that.
Yeah.
Have you seen any?
That's a good question. So I think as far as I'm aware of, uh, that specific type of attack has not been happened in real life, but it can happen definitely. Like when they came up with the concept of a smart grid, there was the same discussion. I just attended like ITS World Congress like last week, and I talk with a lot of DOT people, FHWA people. They know about the problem and they know about the issue, and they know that even though uh, it didn't happen yet, it might happen in the future. The same as other critical infrastructure that didn't happen at the beginning, but later on they started to come up with injecting different type of attacks, or basically raising the concern with cyber attacks. So to answer your question specifically, I'm not aware of that. I'm aware of a lot of different cyber attack on transportation systems. There is a database of that on different type of cyber attacks on CAN system or even computer system of vehicles, but on false data injection on communication, I'm not aware of that. I'm not saying it didn't happen, but I'm not aware of that.
Okay, so it's like more in-vehicle attacks that have happened, but maybe, sorry, do I have time to ask another question, Ali?
Yeah, I think we do, yes.
Okay, have you considered taking a look at ISO 21434 and see if these approaches are somehow relevant in that standard?
Yeah, so that's one of the things exactly we're doing at this point, because we are working with industry at this point, and also some of the I'm not sure if you're familiar with Karma. So we're working with Karma from the FHWA in order to really come up with seeing how our approaches or our algorithms it can be embedded to those standards.
Thank you. Thanks so much.
Can you also, while we are there, and you mentioned of Karma, how is the status of, it looks like that is now is getting slow. It was pretty hot at some point, but then it seems that it was not progressing as the way that it was envisioned. Do you have any kind of where we are heading as far as Karma?
Yeah, so one of the projects that I talk about myself with them is testing security of connected autonomous vehicles, because they are really interested in that. In general, they are interested in testing and verification of Karma platform. As you mentioned, it was really fast at the beginning, and then it slowed down, I think, because of change of administration. And now that we have, I think, Biden's administration, they started to catch up again, especially with this new funding for DOT, which is going to be related to cooperative autonomy and coordinated, let's say, autonomous vehicles. So I think they are trying to improve their work. One of the great things that I saw this time, or basically I talked to them this time, was the fact that they are working on truck companies and commercial vehicles. That was really interesting to me. They are working on that aspect as well.
Okay, great. Thank you.
Armand, what is this web page that you put it in there? RAN?
Yeah, that's my lab, ranks-lab.com.
Yeah, I went there, but I don't see accelerate your digital transformation.
I don't know. Let me check it.
Yeah,
They put it down my website.
I don't know.
Oh,
Maybe
it's working, at least for me. Let me put it in the chat what I
Maybe
see.
project and test management, key project and people.
it's rancs-lab.com. Yep, it's working here. So
But okay,
rancs-lab.com.
maybe go back. Maybe I can, because I'm getting something different.
So I can put it in the chat too.
Yeah, can you do that? Yeah.
Yeah. Let me stop sharing, and then I have to find chat is here. Okay. Yep. I sent it here. Oh, somebody else did it too. Yeah.
Okay, great. So any other question?
Come on, guys. Somebody ask question.
Not this time, but maybe next time when you are driving down, you may pass by and you can see our facility that we have
Sure.
created here. So
Yeah.
it's pretty interesting facility, test track and fleet of autonomous vehicles and so on that we have here.
Sure. So if you guys don't have question, maybe you can talk about your center and facility in maybe a few minutes. I can get more information about it.
Sure, but let's first
Sure.
wrap up this talk and we can continue that conversation slightly after
Sure.
that.
I have a question. I'm
Sure.
Daniel. I'm a grad student under Dr. Carmandini.
Sure.
What has been like your impression of using like virtual simulators? Like how good they are? Do you think it's well spent time pursuing that, or have you really doubled down on real world testing with vehicles?
So for my work and my research, I would say visual simulation, it make more sense because we are attacking different systems and we want to minimize the damage, especially for us. We're not this OEMs. So if our vehicle is damaged, basically we don't have any more funding to replace that. So we just want to reduce the amount of damage. But one of the main problem, I mean, our virtual environment and virtual simulation, it's real time, which is great thing. So when it's real time, it's going to be more realistic. The one that we have, the simulator, the simulation environment that we have, we are using IPG CarMaker. I'm not sure if you're familiar with that. And the software for RPG CarMaker, it has a full vehicle dynamics in it, like it already implemented. And that software we purchased is for almost like $45,000, which is really a high prestigious software as far as testing and simulation environment. Some people I know that they are using Carla. Nothing wrong about Carla, in my opinion, but Carla doesn't have vehicle dynamics. I know also Karma, like a platform, if you work with it, they use Carla simulation software, which doesn't have vehicle dynamics. Everything is just like a dots and they're moving basically with just simple differential equation. It doesn't have vehicle dynamics, which is not going to be realistic as far as I can say. Some other people, they're using different softwares, simulation software, which are not, again, realistic. If we want to really make it more realistic, two things are important. One of them is being real time, like the simulation software running in real time, and also having the vehicle dynamics of other actors or other vehicles to have a vehicle dynamic. So our software, it has it, fortunately, but we had funding. Not all the researchers, they can have this amount of funding in order to have the software. But in that case, real world testing make more sense because it's going to be more accurate and more realistic.
Thank you.
Thank you. So, any other question before we adjourn the meeting? If not, let's thank again Dr. Sargulizadeh, and thank you so much, everybody, and have a great and safe weekend. Stay safe.
Thank you.
Thank you.
Thank you.